Deep in space, hidden behind a veil of dust and gas that made it nearly invisible to previous telescopes, a galaxy is glowing with something extraordinary. Organic molecules, complex carbon-based compounds, the chemical building blocks that, on Earth, are associated with life itself. And the James Webb Space Telescope found them, not in our solar system, not in our galaxy, in a galaxy far beyond our own. Hey space family, welcome back to D3, Discover Deep Dreams, your educational gateway to the cosmos and beyond. I'm your co-captain, and today we are talking about one of the most profound discoveries in the ongoing James Webb Space Telescope mission. Organic molecules, including benzene, methane, and the methyl radical, detected in a hidden galaxy beyond the Milky Way. The first time these specific molecules have been found outside our own galaxy. This isn't just chemistry. This is a window into one of the deepest questions in science. How widespread are the ingredients for life in the universe? Let's explore that. First, let's be clear about what organic molecules actually are, because the word organic gets used loosely and it's worth understanding precisely what scientists mean. In chemistry, organic molecules are carbon-based compounds. Molecules built around carbon atoms, often combined with hydrogen, oxygen, nitrogen, and other elements. Carbon is uniquely suited to forming complex molecules because of its ability to form 4 chemical bonds simultaneously, allowing it to link up with other atoms in an extraordinary variety of configurations. On Earth, organic molecules are the foundation of life. DNA, proteins, carbohydrates, fats, all organic molecules. Every living thing on Earth is essentially a highly organized collection of organic chemistry. But organic molecules don't require life to exist. They form through purely chemical and physical processes. In interstellar space, in nebulae, in the atmospheres of planets, in comets, and in meteorites. We found organic molecules throughout our solar system and throughout our galaxy. What makes this Webb discovery different is where these molecules were found. Not in our solar system, not in our galaxy, in a hidden galaxy far beyond the Milky Way, detected for the first time outside our galactic home. The specific molecules Webb detected are scientifically significant in their own right. Benzene, C6A6, is a ring-shaped organic molecule consisting of 6 carbon atoms and 6 hydrogen atoms. It's one of the simplest aromatic compounds, a category of organic molecules with ring structures that are particularly stable and chemically versatile. On Earth, benzene is found in crude oil and natural gas, and it's a fundamental building block in the synthesis of more complex organic compounds. In space, benzene has been detected in our solar system, in the atmospheres of gas giants like Jupiter, and in the outflows of dying stars. But detecting it in another galaxy is an entirely new frontier. Methane, CH4, the simplest organic molecule, has also been widely detected within our solar system and our galaxy. It's a key component of the atmospheres of the outer planets, exists in vast quantities on Titan, Saturn's moon, and has been tentatively detected in the atmospheres of some exoplanets. Most significantly, Webb detected the methyl radical, CH3, a highly reactive fragment of methane that plays a crucial role in interstellar chemistry. The methyl radical is an important intermediate in the chemical reactions that build more complex organic molecules in space. Finding it in another galaxy tells us something profound about the chemistry happening there. Together, these detections represent the first time these specific organic molecules have been identified outside the Milky Way. The galaxy where Webb made these detections is what astronomers call a dusty starburst galaxy. A galaxy undergoing an intense period of star formation, producing stars at a rate far exceeding what we see in galaxies like our own Milky Way. Starburst galaxies are extraordinary environments. The intense star formation produces enormous amounts of ultraviolet radiation. It drives powerful stellar winds. It enriches the interstellar medium with the products of stellar nucleosynthesis. the elements forged in the hearts of massive stars. And crucially, all that stellar activity drives rich chemistry. The energy from young, massive stars powers chemical reactions in the surrounding gas and dust, building complex molecules from simpler ones. The galaxy was partially hidden because of the enormous amounts of dust associated with its intense star formation. Dust absorbs and scatters optical and ultraviolet light, making the galaxy difficult to study with traditional telescopes. But dust is largely transparent to infrared light, which is exactly what Webb is designed to detect. Webb essentially saw through the dust, revealing the chemistry happening inside this hidden galaxy in extraordinary detail. Here's the profound implication of this discovery. If organic molecules, the building blocks of life as we know it, are forming in galaxies beyond our own, then the chemistry that eventually leads to life isn't a local phenomenon unique to our solar system or our galaxy. It's a universal phenomenon, a natural consequence of star formation and stellar evolution that happens wherever the conditions are right. We've been building this picture piece by piece. Organic molecules in interstellar clouds within our galaxy, amino acids, the building blocks of proteins in meteorites, complex organic chemistry in the atmospheres of other planets in our solar system, and now organic molecules in a galaxy billions of light years away. The picture that's emerging is one of a universe that is profoundly, pervasively organic. A universe where the chemistry of life isn't a rare accident, but a natural consequence of the physical and chemical processes that govern stars, gas, and dust everywhere. This doesn't prove life exists elsewhere. Chemistry and biology are different things. The presence of organic molecules doesn't automatically mean life. It means the ingredients are there. Whether those ingredients assemble into something living depends on a whole cascade of additional conditions and circumstances. But it does tell us that the universe is not hostile to the chemistry of life. It tells us that the molecules we associate with living things form naturally, abundantly, and apparently universally, wherever the conditions allow. This discovery highlights a rapidly growing field called astrochemistry, the study of molecules in space and the chemical processes that create and destroy them. Astrochemistry sits at the intersection of astronomy, chemistry, and increasingly astrobiology, the study of the potential for life beyond Earth. And the James Webb Space Telescope is revolutionizing this field in ways that are only beginning to be appreciated. Webb's infrared spectrograph, the NIRSPEC instrument, is capable of breaking down the light from distant objects into its component wavelengths and identifying the specific spectral fingerprints of individual molecules. Different molecules absorb and emit light at characteristic wavelengths, like molecular fingerprints. Webb can detect these fingerprints with extraordinary sensitivity. This capability has already been used to detect molecules in exoplanet atmospheres, searching for signs of habitability in worlds around other stars. It's been used to study the chemistry of stellar nurseries and planetary formation regions within our galaxy, and now it's detecting molecules in other galaxies entirely. The same technology that might one day confirm the presence of biosignatures, potential signs of life, in an exoplanet atmosphere is the technology that found organic molecules in this hidden galaxy. These discoveries are connected. They're part of the same scientific journey toward understanding whether life is a local anomaly or a universal phenomenon. This detection opens new lines of inquiry that will keep astrochemists busy for years. Scientists will search for these molecules in more distant galaxies, building a picture of how organic chemistry varies across cosmic time and across different types of galaxies. They'll look for more complex organic molecules, moving up the chemical ladder toward compounds even more closely associated with the precursors of life. And they'll continue searching exoplanet atmospheres for the specific combination of molecules that would suggest not just organic chemistry but active biology. The combination of gases that, on Earth, can only be maintained by living processes. We are in the early chapters of this story. Webb has opened a door. What we find on the other side will define the next era of astrobiology. A hidden galaxy, veiled in dust, blazing with star formation, and filled with organic molecules, the building blocks that, on Earth, are the foundation of every living thing. The James Webb Space Telescope found them, and in doing so, it added another extraordinary piece to the picture of a universe that is profoundly, pervasively, universally chemical. We are not an accident. The chemistry that makes us possible is everywhere, in our solar system, in our galaxy, and now, confirmed, in galaxies far beyond our own. The universe makes the ingredients for life. It makes them constantly. It makes them everywhere. What it does with them, that's the question we're still answering. If you like space exploration, don't forget to like, subscribe, and ring that notification bell so you never miss a single D3 episode. Keep looking up.